Thank you, Martin. So before my talk, I need to thank Pablo particularly for encouraging me to do this work as my side project. And also this work benefit from a discussion with Martin, with Pablo, and with Gonda. I will be very grateful if you can provide your comments during the talk or after the talk. If you have any questions, it's totally okay to stop me and ask. So this is so this topic is about a slow sleeve. A slow sleeve has been detected for more than 20 years. Now it's still unclear what the physical mechanism of this slow sleeve and the possible relationship between the slow sleeve and the regular squeak. Now today I'm going to present some new evidence from numerical simulation and from the fractal mechanics theory. And then I will discuss relationship between slow sleeve and regular squeak. And we know when an oceanic plate subducted into a continental plate, at the deep part of the fault interface, the fault keeps steady clipping due to the ductile property of the rock. So at the shallow part of the fault, due to the friction, so the fault keeps locking, and then there are stresses accumulate around the fault. So large megastrut earthquake can release the accumulated elastic energy during a very short period, something like 10 seconds or 100 seconds. The slow sleeve lies occurred between the steady clipping zone and the seismogenic zone. The energy release of the slow sleeve is much slower than the large megastrut earthquake. Because of this slow energy release, we cannot even feel them. So that means we cannot use the seismic station to detect the slow sleeve. And the slow sleeve can only be recognized by the continuous GPS data. And the duration of each slow sleeve range from weeks to years. And thanks to the continuous GPS, to the dense GPS, so now we already have the ability to investigate the kinematics of slow sleeve. So we have found the slow sleeve usually propagate along an elongated fault. That means the rupture of slow sleeve is much longer than it is width. And the most recent observation of the Cascadia slow sleeve have shown that the rupture speed of slow sleeve are quite stable. The rupture speed of slow sleeve is describe how fast the rupture path of the slow sleeve grows along strike. So this they have found the rupture speed of slow sleeve lies between 0.06 to 0.1 meter per second. This speed is even slower than a human walking speed. If we compare the rupture speed of slow sleeve with the regular earthquake, then we can even find that this speed is really slower. It's, in general, the rupture speed of slow sleeve is more than 4 orders of magnitude smaller than the earthquakes. So this wide gap of rupture speed puzzles us by the important questions like what is the possible relationship between a slow sleeve? Is the mechanism, physical mechanism of slow sleeve the same as earthquakes? If they share the same physics mechanism, so there should be a basis model that can reconcile slow sleeve and earthquakes. Actually, this kind of wide spectrum of speed is not a unique phenomenon in the subduction zone. Also, in the universe we live, things can even cover a wide range of speed, from as slow as a snail up to the light speed. The light speed is the limiting speed of the universe. So our understanding of the governed genetic laws for this the thing speed can be divided to 2 parts. So one part is about the Newton's laws. Let's only consider the slow speed, and during this slow speed, the mass is invariant. And later, Einstein's new theoretical theory has discussed about things that can move at an even faster speed, as fast as the light speed. And this theory in incorporating Newton's theory. So one prominent feature in the theory of relativity is that the mass is not a constant. So in the theory of relativity, Lorentz term that controlled the relativistic mass. If the moving speed is much slower than the light speed, so the mass is invariant of the speed. So everything is governed by Newton's laws. But once the speed approach the light speed, so the Lorentz terms dominate the relativistic mass. So this theory actually can incorporate like a unifying theory that can govern all the things in the universe. Actually, this Lorentz term does not only appear in the theory of relativity, it also appeared in the linear electrodynamics. For example, our recent theoretical works has found this Lorentz term also plays an important role in controlling the rupture propagation on the 3D bounded form. So these studies consider a rupture propagate along strike, and the rupture width is confined at the final width. So we have found a new 3D rupture tip equation of motion that can predict the rupture speed in the numerical simulation. And this equation of motion has a very simple form. On the left is a force term. It only depends on the releasing energy and the dissipated energy of the rupture tip. On the right, this is a mass function. It only depends on the rupture speed. And there's a Lorentz term inside this mass function. And the last term is the rupture acceleration. Here, why I say here this equation is a good analog to the Newton's second law, because if the rupture speed is much slower than the light speed, here I found the mass function is invariant of rupture speed. Here on the bottom figure is a mass function. This purple curve shows the apparent mass. If the rupture speed is much slower than the SSE speed, this function is nearly a constant. And this function approach to infinite as the rupture speed approach to the SSE speed. This is a very good analog to the relativistic mass in the theory of relativity. So here, our equation of motion has been well validated by the 3D numerical simulation only for the earthquake rupture speed as highlighted in this orange region. But it is still not clear whether this equation of motion is still valid for relative slow rupture speed like this slow sleeve region. So this is one theory gap that motivated me to try to investigate rupture propagation of slow sleeve. So here, in order to validate this theory, I do some numerical simulation. So in the numerical simulation, I focus on three most important ingredients. So one important ingredient is about frictional behavior. Many laboratory experiments have shown that the frictional behavior of logs may have a frictional transition. That means if the log is moving at a slower sleep rate, then its frictional behavior is velocity weakening. But as the slip rate increase, then the fall frictional can transform from velocity weakening to velocity strengthening. So they have found this frictional transition is very important to explain the observation in the laboratory, and also they have found it's necessary in a numerical simulation to try to obtain a slow sleeve event. But here, in this work, I'm going to use a simple latent state friction, but with such frictional transition. So on the right, this sketch shows this steady state strength curve. So here, there's an important quantity parameter, that's critical slip rate. If the slip rate is lower than this critical slip rate, then the fault has velocity weakening behavior. That means A minus speed is negative. If the slip rate is higher than this critical slip rate, then the force strength friction becomes velocity strengthening. And also here, the critical slip rate is one parameter I'm going to vary systematically. And then the other parameter is the stress drop. So the stress drop depends on the initial shear stress. I mean, if I set up a higher initial stress, then the final stress drop will be larger. So I only systematically value two parameters. Yeah. So the other two ingredients are about the dynamic waves and the fall geometry. We know if the rupture speed is very fast as the SW speed, we know the rupture will release very strong seismic radiation. So in this case, full dynamic simulation are necessary to capture the dynamic wave effect. But for the rupture propagation of slow sleeve event, so the seismic radiation is negligible. So I use the quasi-dynamic simulation to simulate the rupture of slow sleeve. And for both slow sleeve and earthquakes, this rupture usually propagate along on elongated fault. Means the fault length is much longer than its width. So here we must need to account for finite fault width. And in the simulation, where I consider a single rupture model rather than cycle model. So here, as I mentioned, I only vary two parameters. One parameter is the critical slip rate, and another parameter is the stress drop. Yeah, I found even turning these two parameters, I can get a full spectrum of rupture speed in a numerical simulation. So the rupture propagate outside the nucleation zone, and the rupture can obtain a steady speed very fast. And the steady rupture can range from as slow as this slow sleeve up to the SW speed. So in order to investigate the relationship between the slow sleeve and the earthquakes, here I compare the dependency of the steady ruptures on the peak slip rate. On this left figure, the vertical axis is the peak slip rate, and the vertical is the steady rupture. And this diamond samples indicates the result from the slow sleeve event, and this stars indicates the model result from for dynamic simulation of the earthquakes. So here, this color indicates different value of slip rate. And here you can find for given the same critical slip rate, in general, the steady rupture speed increases with the peak slip rate. And as you increases the critical slip rate, you can find, you can just simply like offset all this result upward as you increases the critical slip rate. And that means these trending are very similar to each other. And also it's also very similar for between the slow sleeve one with the earthquakes. Here the earthquakes comprise of two different speed range. Here I define if the rupture speed is much close to to the earthquake speed. So I defined it as the fast earthquake. Here, there's a special kind of earthquake. It's called a tsunami earthquake. The tsunami earthquake, the rupture speed are around 1/3 of the earthquake speed. Here you can find even the slow sliver share a similar trending with this kind of tsunami earthquakes. But once we see a fast earthquake region, you can find this the trending changes due to the limiting of the earthquake speed. This is because Lorentz turn plays a role in here. This is like this is analog to the theory of relativity. If things move at a speed close to light, it becomes the metric of the speed space is not linear anymore. So in order to account for this Lorentz factor, on the right figure, I consider the rupture speed divided by this Lorentz term. So after this, after accounting this effect, I found this trending, this general dependency of rupture speed to the peak slip rate. I even see similar between fast earthquake and the tsunami earthquake, and also similar with the slow sliver. If I normalize all this rupture speed by the critical slip rate, you can find all this simulation include earthquakes, fast earthquake, tsunami earthquake, and slow sliver. They all will collapse onto a single curve. And also this single curve can be predicted by 3D theory of dynamic fraction mechanics. And here, this shows the numeric simulation result, the consistency of the numeric simulation with the theory has shows that slow sliver, a physical mechanism of slow sliver are the same as the regular earthquakes. So actually, this static rupture can also be predicted by the 3D fraction mechanics theory. So if a rupture can propagate at a steady speed, that means it is rupture acceleration is 0. So on the bottom this is an equation of motion for earthquakes. So if the acceleration is 0, then this equation can lead to an energy balance equation. That means for rupture that propagate at a constant speed, it is releasing elastic energy need to be exactly balanced by the dissipated flux energy. Yeah, this is intuitively reasonable. But this energy balance is not the only condition that can guarantee the steady rupture, because the steady rupture still need to have some like resistance to any perturbation. So based on the stability analysis, I derive another stability condition. So the meaning of this equation is that as the rupture speed increases, the dissipated energies need to increase faster than the increases of releasing energy. So this is like there's a negative force that can drive back any perturbation, and this is like a damping effect. And all these two conditions can be demonstrated on the right sketch. In this sketch, this blue curve shows the dissipated energy, and this orange curve shows releasing energy. So the energy balance condition can be satisfied at least two intersection points, because at least 2 points their energy are the same. But only the right point is the stable solution. This is because this point also satisfies the stability condition. That means at this point, as the rupture speed increases, the dissipated energy increases faster than the releasing energy. And these two stability conditions are really generic for. It doesn't depend on any special friction law. That means even for any given friction law, as long as these two conditions can be satisfied, so then this theory can quantitatively predict the rupture speed. And also the condition doesn't depend on the absolute value of rupture speed. That means if you can offset horizontally move this curve to any speed, so this theory also valid. So here I'm in my numeric simulation, so I can calculate the value of fracture energy and the releasing energy to validate this theory. So on the left figure shows the result of fracture energy and the releasing energy. Here you can find for all the simulated model, the fracture energy is always the same as the releasing energy. It means this result has validated the first energy balance condition. So on the right figure, it shows the dependency of the fracture energy on the peak slip rate. Here the vertical axis is the peak slip rate, but actually it is interchangeable with the rupture speed because the rupture speed is increases with the peak slip rate. So the right figure shows the fracture energy increases with the rupture speed. And also in this simulation, the stress drop in the model is a prescribed parameter. That means as the rupture speed increases, the energy release rate is always a constant because it is prescribed. So that means these two, the right figure have validate the second stability condition. As the rupture speed increases, fracture energy increases faster than the dissipated energy. So here I'm going to show you another slide that I have presented in my last talk last year. So I'm not going to repeat this result. I'll just briefly say what we found. So in this work, we have found the rupture propagated on 3D long fault can be at any continuous speed from the S-wave speed to the P-wave speed. So adding this part of work with my most recent work, now I can conclude the rupture propagated on 3D long fault can propagate at any speed from as slow as the slow sleeve up to the P-wave speed. And also the energy balance and the stability conditions are generically valid for this case, no matter whether there's the dynamic waves or there's no dynamic waves effect. All these works previous work are about steady rupture. And now I'm going to present some further evidence of non-steady ruptures. So here I consider a piecewise constant distribution of initial stress. So here I consider that the rupture propagated from segment 1 to segment 2. The initial stress of the segment 2 is higher than the segment 1. So I expect the rupture transform from one steady state up to another steady state. And here you can find the rupture speed curve transform to one state to another state requires a transition distance. And these gray curves are the numerical result of slow sleeve one. And these color curves are from the result of dynamic earthquakes. And you can find this transition distance is the shortest for slow sleeve one. And also it is shortest for the dynamic earthquake, but whose rupture speed is only a small fraction of the S-wave speed. And as the rupture speed approach the S-wave speed, you can find like this curve shows, the rupture requires a longer distance to transform from one state to another state. So this is because when the rupture speed approaches S-wave, the Lorentz time plays an important role in controlling rupture acceleration. From this result, you can also find transition curves of slow sleeve are quite consistent with with low earthquake whose rupture speed is only a small fraction of the S wave, like a tsunami earthquake, you can find that their transition curve are very similar to each other. So this is the first case, and in another case, I consider the rupture propagated into a barrier. So the barrier is a 4-segment and that has initial shear stress lower than the minimum condition that can guarantee a steady ruptures. So when the rupture propagated into this barrier, its rupture slows down until finally stops. Here I consider how far this rupture can penetrate into this barrier. So here on the right figure, this diamond shows the result from the slow sleep event, and these stars are result from the dynamic earthquakes. Here you can find if the rupture speed of the earthquake is only a small fraction of the S wave, like this trending. You can find that there's the trending, the dependency of the last distance on the peak sleep rate are the same as the slow sleep one. But as the rupture speed approach the S wave, you can find it apparently depart from the general trending. Also, this is because of the dynamic wave effect. And also here you can see the non-steady state rupture of slow sleep resemble the slow earthquake, like tsunami earthquake, but depart from the fast earthquake. I provide a mechanical explanation to explain why the transition or last distance of fast earthquake is longer than the slow sleep event. Here I rewrite the equation of motion I mentioned earlier about earthquake ruptures. So here the rupture acceleration is the ratio of this force turn to this mass turn. And this force turn is a function of the dissipated energy and releasing energy of the rupture tip. This turn depends on the frictional response. Because in this study, I fixed the friction law for both slow sleep and fast and earthquakes. So this turn can be seen as a fixed constant. Only the difference that control the non-steady rupture is this term is a mechanical term. It depends on rupture speed. This term, as I plot on the bottom figure, this term is a constant if the rupture speed is much slower than the S wave speed, and also include slow sleep and the tsunami earthquake. So that can explain why the rupture transition curve of the slow sleep are so consistent with the slow earthquake like tsunami earthquake. But as if the rupture speed approach the S wave speed, it's the Lorentz terms plays a significant role. That will make this mass become much larger. So if the mass is larger, that means the acceleration, if given the same force, then the acceleration is reduced. That means the rupture requires a longer distance to transform from one steady state to another steady state. And also this explanation is valid for the another case about the barrier case. So now here all this evidence of steady and non-steady rupture have shows that rupture mechanism of a slow sleep event are the same as the regular earthquake. Here the slow sleep event just can be seen as a special case of earthquake only when the Lorentz term is not significant. So the scaling relation between the moment and the duration, seismic moment and the seismic duration, has been viewed as a tool to try to differentiate the physical mechanism of slow sleep and earthquakes. So like So they have the previous observation have shown that the moment duration scaling of the regular earthquake is cubic scaling. And an earlier work in 2007 on the left figure shows they compile the global observation of slow sleep, and they found the moment duration scaling is linear. And then they suggest the physical mechanism of the slow sleep is different from a regular earthquake. But recently observation that focus on a particular environment, they have found the moment duration scaling is not a linear, and instead is a cubic relation. And then they suggest the physical mechanism of slow sleep is the same as the earthquake. But this debate is still ongoing as more and more different exponent coefficients are proposed. Like someone proposed the scaling relation between moment and duration is something like 4 or 3, and many different coefficients. Now here, I found this scaling relation actually relies on some strong assumption. For example, this scaling requires the rupture speed and the stress shocks is invariant for different seismic moment. Here, let's consider a special case like for a particular environment data, particular data set. If we assume their critical sleep rate is a constant, so my numerical simulation has shown that if this critical sleep rate increases, then the rupture speed increases. So that means rupture duration will decreases. Oh, that means if this data set has different value of critical sleep rate, actually you can move this local data set upward or downward. And if you try to derive a slope of this scaling relation, then you can still get the same scaling, because if you just move this data set upward. So this is okay for regional data. But if you're trying to add like global data set, that's because different environment may have different critical sleep rate. That means you can add some different value. So if you try to get some scaling from this global data set, that seems not so meaningful. So here I proposed a different scaling. I can try to understand the relationship between slow sleep and earthquake. Here I collect the global data set of slow sleep, include the Cascadia event and also the Japan slow sleep. And here I also include the global tsunami earthquakes. Here I present the scaling relation between the average rupture speed with the peak sleep rate. Here I simply calculate the average rupture speed by the ratio of rupture length to rupture duration. So yeah, this is a simple estimate. If the rupture is bilateral, there should be an error of factor 2. Here I estimate the peak sleep rate by this empirical equation. So the average sleep rate is the ratio of the final sleep to the rise time. And here the rise time is depends on the rupture duration, rupture width, and the rupture length. And here I use this is the 20. The number 20 is an empirical factor that was obtained from the numerical simulation. This factor links the peak sleep rate with the average sleep rate. By calculating this to quantity of the rupture speed and the peak sleep rate, on the left figure shows this the result from the global data set. Generally, you can find the trending of the average rupture speed increases with the peak sleep rate. And both the data from the slow sleeve and the regular earthquake are lies between two theoretical as predicts. And this two theory predicts is about with a constant strength drop. And the strength drop is 0.5 megapar and 0.05 megapar. And in order to see whether to compare this result with the theoretical predict, here I need to assume the value of the critical sleep rate. Here I assume the critical sleep rate for the slow sleep is to be minus exponent minus 7 meter per second, and I assume the value of the tsunami earthquake is different. So by assume this parameter, I found all the data set of the slow sleeve and the regular earthquake they can well fit with the theoretical predicts. And actually here I can get a better fit by using like a least square method to better constrain the critical sleep rate. But anyway, this result has already shown that the physical mechanism of the slow sleep are quite consistent with a tsunami earthquake, even from the global data set. And in my next step, I will try to better constrain the critical sleep rate for different subduction zones. What can we learn from this new evidence or these new conclusions? We have known that slow sleep can usually occur at different or separated for segment independently. But some slow sleep can bridge multiple segments and forms a much larger magnitude. So I call this large magnitude as like a supercycle slow sleeve. Actually, this behavior is very similar to the concept of supercycle earthquake. So on the right figure, it shows the historical earthquake that occurred on a very long subduction zone. And from this historical data, you can also find the rupture in the history only rupture at different separated segment. But some huge earthquake, a super huge earthquake, can bridge multiple segments and form a super huge earthquake. That is called a supercycle earthquake. But unfortunately, limited by the observation period for the large magnitude earthquake, we cannot look at the complete picture of this supercycle. That's because the earthquake intervals of magnitude earthquake is very long, something like 10 years or 100 years. But here, because the mechanism, physical mechanism of slow sleep is the same as the regular earthquake. That means we can focus more investigation on the supercycle behavior of slow sleep, like the figure shows on the left, because the interval of slow sleep are much shorter than the earthquake, something like a week, range from weeks to years. That means we can collect more data from slow sleep, and we can build up a bigger picture from this like upscale template. And then this result may help us to better understand the earthquake behavior that covered a longer period. So this is just one new perspective that we can learn from this result. And another one is from how can we use the data of slow sleep that can help us to assess the future earthquake size. Yeah, actually I have presented this slides in my last talk last year, but here I'm going to repeat this. So in this work, we have develop a new method to assess the future earthquake size. So the essence of this method is we need to obtain a scaling relationship between the fracture energy and the final sleep, like the left figure shows. If we can obtain a robust scaling relation between them, then we can combine this result with seismic coupling levels obtained by the continued GPS observation. And if we combine these two observations to result, then we can predict the potential future earthquake size. But the large uncertainty in this method is that whether we can obtain a robust scaling relation between fracture and final sleep. And that is limited by the finite data set from the large maxilla earthquake. But since the slow sleep event, the physical mechanism of slow sleep event is the same as the regular earthquake, that means in the future we can investigate the dynamics of the slow sleep event. Then we can collect frictional parameter from the slow sleep event that happen much more frequently than the large earthquakes. Then we can add the slow sleep event data to the earthquake data. Then we may obtain a more reliable scaling relationship that may in return help us to assess the future potential earthquakes that occurred on the subduction zone. So here is the summary of my talk. So the mechanism of slow sleep, I have found the mechanism of slow sleep are the same as the regular earthquake, and I provide numerical and analytical evidence to show that. And also this model opened new avenues for future investigation of the frequently occurred slow sleep, which in return can help us to advance our ability to assess future seismic hazard. So that's all about my talk. Thank you for your attention.